everyone. Today we're going to start Module 7, which is all about gases. So this is going to cover Chapter 8 in your textbook. So I don't have individual sections listed because we're only covering sections in Chapter 8. Now we're just briefly going to discuss gases because once you get into general chemistry, there's a whole chapter devoted to gases as well. So you'll get to see this information in the future too. So the first thing we should talk about is something called kinetic molecular theory. And this is a theory that describes gases and how they behave. So according to this theory, a gas consists of small particles that move randomly with high velocities, and that's something we've talked about before. So when we talked about solids, liquids, and gases, we saw that gases move really quickly. They're very energetic. Now, number 2 here, gases have very small attractive forces between molecules. So if we think about a solid or a liquid, the particles in a solid and a liquid are very close together, and they likely have attraction for each other. But in a gas, it's the opposite. The particles are really far apart, and we're going to assume that they're not attracted to each other. So, for instance, we won't see those two particles coming closer together due to any sort of attraction. They're just going to remain separate. All right, number 3, gas particles occupy a much larger volume than the volume of the molecules alone. So remember when we talked about gases previously, we said that the particles were really far apart because gases fill up the container that they're in or the room that they're in. So if we were to take each of these particles and figure out their volume, it would be much, much smaller than the total volume that they occupy. So we could compare the volume of all of those particles to the volume of the container that they're in. All right, and then number 4, we're going to assume that gases are in constant motion and they move rapidly in straight lines, unless they hit something and then they'll move in another direction. And then 5, they have a temperature in units of Kelvin that's proportionate to the average kinetic energy of the molecules. So really all that's saying is that kinetic energy, which is the energy of movement, is proportional, so that's our symbol for proportional, to the temperature or the average temperature of the gas. So for instance, if we increase the temperature of a gas, that's going to give each of the gas particles more energy overall. If we were to cool down the temperature of the gas, then those gas particles would decrease in energy. So that's all that's saying there. Now, the kinetic molecular theory assumes that gases behave in this way. Not every gas does behave this way. Some gases are really large, so then number 3 wouldn't necessarily be true. For instance, if we look at the noble gases, argon and krypton are actually very large gas particles. So number 3 might not always be true. It just depends on the gas. And then in number 2, we said that gas particles have very little attraction for each other or repulsion. But some gases can react with each other. It just kind of depends on what gases you're looking at. So as an example, in our atmosphere, there are reactions going on between gases all the time. Um, between greenhouse gases, between, just normal everyday gases. So that's not necessarily always true that they have very little attraction for each other. But we're just going to assume that the kinetic molecular theory is valid as we move through chapter 8, and that's going to make things much simpler. All right, so there are 4 properties that we use to describe a gas, and those 4 properties are pressure, which has the symbol capital P, volume, which has the symbol capital V, temperature, capital T, and amount, which is lowercase n. And that usually stands for moles. All right, so in your textbook, there's table 8.1, and this kind of goes through each of those 4 properties and defines them, as well as lists the units of measurement. So if we look at pressure, this is defined as the force exerted by a gas against the walls of the container. So for instance, if we go back to that figure we were looking at on the last slide, you can see that these gas particles are moving around, and then some of them are hitting the walls and bouncing off. So when those gas particles hit the walls of the container, or maybe each other, they exert a pressure when they collide with either the wall or each other. And that buildup of pressure is what we're referring to. So it's really a force. Now, there are a lot of different units we can use for pressure, and we'll talk about those later. Volume is defined as the space occupied by a gas. So we've talked a lot about volume this quarter. And the units of measurement are liters and milliliters, which we're used to by now. Temperature is, again, related to the energy of the gas. And we're going to use Kelvin in particular. Now, you can report the temperature of a gas in Celsius or Fahrenheit, that's fine. But when we do calculations with gases, we always use Kelvin. And we'll talk about why later on. And then last, we have amount. And you could express this in grams, but most often we're going to express this in moles. Okay. So let's talk a little bit more about volume. So again, the volume of a gas is the same as the volume of the container it occupies. It's usually measured in liters or milliliters. And the volume of a gas will increase with an increase in temperature at constant pressure. So if, for instance, let's say we could move this lid of this container up and down. If we increase the temperature of the gas in that container, the particles are going to exert a constant pressure, we're assuming, but in order to keep the pressure the same, we have to increase the volume of the container. So those gas particles would push that lid up so that they can occupy a greater volume. And we'll talk more about that later too. All right, temperature. So again, remember, temperature relates to the average kinetic energy of the molecules. So we could write that kinetic energy is proportional to temperature, and that's the average temperature of the gas. Now, again, as I said earlier, this is going to be measured in Kelvin. So we'll be using that Kelvin scale. Now, when the temperature of a gas is decreased, we're decreasing the energy of the gas. And that means that molecules of a gas are going to have fewer collisions with each other and with the walls of their container. Now, if we increase the temperature of a gas, we're increasing the energy of the gas. So that means the molecules are moving around more rapidly, so there's more opportunity for them to collide with each other and with the walls of their container. Okay. Now, pressure is another factor here. So again, pressure is a measure of the gas particle collisions with sides of a container. Now, this can be measured in multiple units. So for instance, we have a unit called millimeters of mercury. So that's abbreviated mmHg. And remember, Hg stands for mercury. And so we'll talk about this particular unit a bit more in a couple seconds here, but this is kind of a strange unit just right out of context. We also have atmospheres, which is abbreviated ATM, and then pascals or kilopascals. So kilopascals is just a larger unit related to pascals. And then this one you might be familiar with, pounds per square inch, or PSI. That's usually the pressure we use for tires. So this unit you might have seen before if you filled up your tires. Now, the reason pressure is so important with gases is pressure can have a huge effect on the other variables we talked about. So as an example, gas particles in the air around us exert pressure on us, and that's called atmospheric pressure. So over on the right, you can see this guy is standing on the Earth, and atmospheric pressure is pressing down on him. Now, this isn't a huge pressure by any means. I mean, we can still walk around and, do stuff, but it's definitely a measurable pressure. Now, remember, air consists of a mixture of gases. So in air, we have 21% oxygen, 78% nitrogen, and then the other 1% consists of other gases like CO2, argon, etc. But those gases are exerting a pressure on us every day. Okay, so let's talk about that weird unit, millimeters of mercury. So the way that we typically measure the pressure that the atmosphere exerts on us is by using something called a barometer. So a barometer, again, measures the pressure exerted by the gases in the atmosphere. So oxygen, nitrogen, and then the other 1% of gases. Now, a barometer, at least an old school barometer, measures atmospheric pressure by using mercury in a column. So off to the right, you can see we have liquid mercury in a pool here, and it's traveling up this column, and it's traveling up that column due to the pressure that atmospheric gases are exerting on the mercury. So what we do to figure out the pressure of the atmosphere is we measure the height of this column of mercury. So normally, if you're at sea level, atmospheric pressure is equal to 760 millimeters of mercury. So if we measured the height of this column, it would be 760 millimeters, and then we just add mercury on the end. So that's where that unit comes from. Okay, so if the atmospheric pressure is equal to 760 millimeters of mercury, we say that that is 1 atmosphere of pressure. Okay, now there is another unit, torr, which is exactly equal to millimeters mercury. It's just named after Evangelista Torricelli, who invented the barometer. So this is just to kind of acknowledge Torricelli's work. Now, remember, these are equalities, so later on we can turn these into conversion factors. So we'll use that later. Now, at TCC, we do have a mercury barometer in one of the hallways by the labs. I really wish I could have shown it to you because it is a really cool device. But nowadays, we have watches that tell us the pressure of the atmosphere. We have, our devices will tell us the pressure of the atmosphere. But sometimes it's nice to just go back to the original way of figuring these things out. So if you ever do get to go back to TCC in person, see if you can find that mercury barometer. Okay, and then in your textbook, there is a table of these different units for measuring pressure. And you can see there are a ton of different ways we can measure pressure or express the amount of pressure. Now, most often in chemistry, we're going to use atmospheres and millimeters of mercury. So don't worry too much about these other pressures. Maybe torr, because torr is equal to millimeters of mercury. But the other types of pressure here, the other units of pressure, won't be used as often. Okay, so we just talked about how the atmosphere exerts a pressure on us. Now, this does change depending on your elevation. So if you're at sea level, atmospheric pressure is approximately 1 atmosphere, or 760 millimeters of mercury. However, if you were to climb up a mountain, the amount of gas decreases, or at least the pressure of the gas decreases. So air kind of thins out as you go up in altitude. So for instance, at the top of this mountain in the picture, atmospheric pressure has decreased to 0.7 atmospheres, or 530 millimeters of mercury. So if you've ever hiked a mountain, or let's say you've gone skiing or snowboarding, and you've gone to the top of a mountain, you might have noticed it's a little harder to breathe at the top of that mountain. And that's due to the elevation, because the gases are thinning out, there's not as much oxygen present, and again, atmospheric pressure decreases. So sometimes you can get what's called altitude sickness. I know I experience it. I'm very sensitive to it. One time I went to Colorado, and we went up into the mountains, and oh my gosh, I felt so sick for the entire time I was there. So the higher up in altitude you go, the less oxygen there is, and that can make you feel kind of dizzy or ill. And it does take a while to acclimate to that. So if you've ever experienced that, that's why. So for instance, down below we have table 8.3, and we have different places here. So sea level, Los Angeles, we've got Denver, which is the mile-high city, and you can see that the altitude is changing as we look at these different cities, and the pressure is changing as well. So at sea level, again, we expect an atmospheric pressure of 760 millimeters of mercury, or 1 atmosphere. And Los Angeles is a little bit higher than sea level, and you'll notice that atmospheric pressure is a little bit less, at 752. Then if we go to Denver, which is the mile-high city, so it's a mile up, atmospheric pressure in Denver is about 630 millimeters of mercury. Now Mount Everest, which is super tall, the atmospheric pressure at the top of Mount Everest is 253 millimeters of mercury, so that is an extremely small pressure. at least compared to sea level. Now, the Dead Sea is actually below sea level, and the atmospheric pressure there is much higher than at sea level. It's at 800 millimeters of mercury. So just kind of interesting that atmospheric pressure does change with elevation. Now, atmospheric pressure also changes with variations in weather. So if you are, experiencing a hot, sunny day, that's actually going to cause a higher atmospheric pressure. And then if you have a colder, maybe more rainy day, that's going to result in less atmospheric pressure. And I've actually seen this with the mercury barometer at TCC. When we do labs related to gases, we go and check the pressure on the barometer. And I've noticed on rainier days, the pressure is lower. And so the mercury column is lower. So the height of that mercury is lower. And then on hot, sunny days, the height of that column is higher, or the pressure is higher. So just kind of interesting that, weather can affect the pressure as well. Okay, so let's do a couple of practice problems here. And we're going to use that equality where 760 millimeters of mercury is equal to 1 atmosphere. So what is 475 millimeters of mercury expressed in atmospheres? So this is a pretty simple conversion. We've done this before. We're going to start with what we know, or what we're given, and then we're just going to fill in our conversion factor. So in this particular problem, we're trying to convert millimeters of mercury to atmospheres. So we're going to put 1 atmosphere in the numerator and then divide that by 760 millimeters of mercury. All right, and what should that give us? Okay, so we know that this is not a direct relationship, so we can cancel out A. And C is quite high, and we're just taking 475 and dividing that by 760. So C is likely not our answer. So it would be B. And of course, you can verify that on your calculator. Okay, what about number 2? If you want to try this one on your own, you can pause the video, and then we'll go over that together. So in number 2, the pressure in a tire is 2 atmospheres. What is this pressure in millimeters mercury? Okay, so again, we're going to start with what we're given. And then we're going to flip our conversion factor, right? Because now we're going from atmospheres to millimeters of mercury. So we're going to put 760 millimeters of mercury in the numerator, and we're going to divide that by 1 atmosphere. Okay, so we're multiplying 760 by 2, so that should give us 1,520 millimeters of mercury. All right, so not too bad. You might have to do this conversion a few times depending on what units are given, and you might need to use atmospheres instead of millimeters of mercury or vice versa, so this is good to practice. Okay. So we'll end the video there. Next time, we're going to start getting into gas laws. So these gas laws will tell us the relationships between those 4 variables we talked about. So we'll look at the relationship between volume and pressure, pressure and temperature, volume and temperature, etc. And we'll see how they affect each other. So I will see you then.